Hello, I'm Doug Waples. Welcome to a video that presents my ideas about how to best define the oil generation window, and particularly the role that source rock kinetics can play in this process. This video isn't intended to be an introduction to Kerogen Kinetics, but you won't need to be an expert or a specialist to follow the discussion. As with many topics, it is, I think, useful to begin with a historical perspective. We'll begin by mentioning some of the numerous methods that have been used to define generation windows since the early days of petroleum geochemistry. The first method for defining the hydrocarbon generation window was the carbon preference index, or CPI, determined from the normal alkane distribution in source rocks or in oils. This gas chromatogram of an immature rock extract shows a strong preference for the odd carbon normal alkanes in the waxy range. In contrast, this gas chromatogram of the saturated hydrocarbons from an oil shows a much weaker preference for the odd carbon members and therefore indicates a higher level of maturity. Unfortunately, the CPI was neither highly quantitative nor highly accurate, and it was soon replaced with the thermal alteration index, or TAI, which was based on changes in the color of kerogen, particularly bisaccate pollen grains, with increasing thermal stress. We see here pollen grains changing from a yellowish color through orange to brown to finally black with increasing maturity. By the late 1970s, vitrinite-reflectance had largely replaced TAI as the dominant method of assessing hydrocarbon generation quantitatively. And that has remained the dominant technique until pretty much the present day. Here we see a histogram of measurements of vitrinite reflectance on a large number of particles in a single sample. A statistical analysis is carried out on all of the measurements that were made, and a single average number is chosen, as shown here, 0.53% vitrinite reflectance. Vitrinite reflectance is well known to correlate well with other properties of kerogens and coals, and to increase steadily with increasing thermal stress of the kerogen. A major limitation of all of these techniques is that they are proxies for actually measuring hydrocarbon generation. You measure some property that was affected by the thermal stress and try to relate that in some way to the process of hydrocarbon generation, which is a quite different process. With the advent of basin modeling and source rock kinetics, it became possible from the mid-1980s onward to calculate hydrocarbon generation directly and to use the transformation ratio as a direct measure of hydrocarbon generation. Transformation ratio has a value of 0 when any kerogen is fully immature, and a value of 1 when that kerogen is completely exhausted. But problems arose because users were reluctant to move away from vitrinite reflectance as the standard indicator of hydrocarbon generation. We could calculate transformation ratio, but people still wanted their oil windows defined in terms of vitrinite reflectance values. As a result, in 1998, Roger Marzi and I published a paper seeking to clarify some of the issues related to this equivalency between vitrinite reflectance and transformation ratio. This plot shows the relationship between vitrinite reflectance and transformation ratio for several different kerogens taken from published data. And it's very clear that there are very different relationships for different kerogen types. In this plot, vitrinite reflectance and transformation ratio are both calculated values. They were calculated using a geologic heating rate of 3 degrees Celsius per million years. To calculate vitrinite reflectance, we used the standard Lawrence-Livermore easy percent RO kinetics, which were the same for every kerogen. While for the transformation ratio, we used the published kinetics for each individual kerogen, which were different. If we want to interpret our diagram in terms of an oil generation window, we have to define the beginning and end of that window. Many years ago, the French Petroleum Institute started defining the beginning of significant oil generation as a transformation ratio of 0.1. And that value has been widely used. So that's what we'll use here. That is indicated by the two black arrows and shows that the beginning of significant oil generation in this example could be as early as vitrinite reflectance value of 0.55 or as late as a vitrinite reflectance value of 1.05. That's quite a range for the beginning of oil generation. Similarly, if we define peak oil generation as a transformation ratio of 0.5, we see that the vitrinite reflectance value could be as low as 0.77% or as high as 1.2%. Finally, if we define the end of oil generation as a transformation ratio of 0.8, taking into consideration that the gas proportion in most good quality kerogens is assumed to be 15 to 20%, then we see that the end of oil generation could occur at as early as a reflectance value of 0.9 or as late as a reflectance of about 1.3%. Our original objective in writing this paper was to show people that you couldn't define the oil generation window using a standard set of vitrinite reflectance values that would apply to all kerogens. Instead, the vitrinite reflectance values at which oil generation began or peaked or ended would depend on the kerogen type. But the study had two weaknesses. It focused on helping people use RO more realistically to define hydrocarbon generation windows, instead of convincing them to abandon RO entirely as the standard and adopt transformation ratio as the common language. And the second mistake was it trusted the published source rock kinetic data too much. In basin modeling, calculation of hydrocarbon generation is done using the Arrhenius equation, where the reaction rate constant K depends both on an A factor and on the activation energy, both of which are shown in the equation in red. However, the multi-run method for obtaining the A factor and the activation energy distribution has been severely criticized since the early 1990s as being unable to fully separate the effects of A and E. The consequence is that although you can obtain a single best A-E combination, that combination doesn't fit the pyrolysis data significantly better than an infinite number of other possible A-E combinations that fall along what is commonly called the compensation line. This diagram in 3 dimensions shows the log of the A factor plotted on one of the horizontal axes and the activation energy on the other horizontal axis. And on the vertical axis, we have the quality of fit between the measured pyrolysis data and the values calculated using the AE combinations we supply. The deep trough in the middle represents the minimum trend of error. That is, the amount of error increases upward in this diagram. So we're looking for a solution somewhere in that trough. The best mathematical solution is shown by the red arrow, but it is not significantly better as a solution than many other points along the compensation line or even other local minima as shown by the other low points in the diagram. The red arrow here points to another solution which is almost identical statistically and yet has different A and E values. These red arrows indicate other points along the compensation line, not in the deepest part of the trough, but still a very, very good fit to the measured data and something that should be considered as a viable solution to the question of what is the correct A, what is the correct E for this pyrolysis. This diagram shows the compensation lines for 3 different kerogens. Any point along any of those lines will give essentially the same quality of fit to the pyrolysis data from the laboratory as any other point. Consequently, the choice between any points along any compensation line is effectively arbitrary. If you are interested, these are references relevant to the question of reliability of A and E data obtained from multi-run kinetics if A is allowed to vary freely. Simply stated, the compensation effect occurs because the same value for the reaction rate constant K can be calculated using an infinite number of combinations of A and E, as shown by this equation. If you double the value of A, for example, in order to compensate, E must increase by approximately 1 kilocalorie per mole. And that is because if you increase A, the reaction will go faster. And to compensate for that increase and keep the calculated value the same, you must also increase E in order to slow down the rate. So as an example, suppose a reaction has an A value of 2E14 per second and an activation energy of 54 kilocalories per mole. The rate of the reaction would be the same if we used twice the value of A, that is 4E14, and simply increased E by 1.04 kilocalories. Or if we lowered A by a factor of 2 and reduced the activation energy by 1.04 kilocalories. This histogram represents a compendium of the logs of A factors obtained from about 250 kerogens from published sources. These were all obtained using multi-run kinetics with the A factor varying freely. We could see there's a very wide range of A factors, nearly 10 orders of magnitude, but that most of them would fall within about 2 orders of magnitude of the mean, which is about 1.6 E14. This distribution, which appears to be approximately log normal, that is, the logs of the A factor are normally distributed, suggests that A is controlled by some combination of natural variation in kerogen type and by various uncertainties in obtaining and analyzing the data. But before we go too far in interpreting the distribution of A factors, let's first look at the implication for hydrocarbon generation of using this wide a range of A values and their corresponding activation energy distributions. This plot shows calculated vitrinite reflectance values plotted against calculated transformation ratios for approximately 250 kerogens whose kinetics were determined using the standard multi-run method with A allowed to vary freely. If we zoom in on the same plot and superimpose interpretational lines, the red lines show the entire range of values at the beginning, peak, and end of oil generation, whereas the yellow lines represent the great majority of the kerogens. The total range of variation at each threshold is huge on the red lines, approximately 1% RO difference between the fastest and the slowest kerogen. However, the variation of most of the samples falling within the boundaries of the yellow line is more like the range that we saw in the example published by Waples and Martzi, which is about 0.5% RO. Here again is our original published diagram showing that the range that we proposed in 1998 for the windows of about 0.5% RO based on limited samples is similar to that we showed on the previous diagram for the great majority of the samples. However, there are many samples that fall outside this range and that therefore would generate at quite different maturity levels than even the ones we proposed here. So a logical but tentative conclusion based on analysis of the published kinetic data is that the oil generation window is very, very wide when we look at the entire range of kerogen types and composition. And therefore, natural variations in kerogen type and in our knowledge of kerogen composition in specific source rocks represent potentially large exploration risks. As I said earlier, the kinetics database used in this study included about 250 samples, and those were from about 100 different source rocks. However, many of these source rocks had multiple samples. We paid particular attention to 11 source rocks that each had been analyzed between 8 and 22 times in publications, sometimes only within a single laboratory and other times by multiple laboratories. The source rocks with many different analyses are particularly valuable for us because they're going to teach us about variation in results from one laboratory to another, from within a single laboratory, and the differences between very different types of source rocks. Here are the 11 source rocks that we identified as having a large number of analyses. There are many very familiar names on here, such as the Bakken, the Kimmeridge Clay, the Monterey, the Green River Formation, but a few others that are less well known. Of particular importance for this presentation are the ones shown in green at the bottom, the 5 down at the bottom, because they represent a wide range of kerogen types, type 1, 2, and 3, and therefore enable us to generalize our conclusions quite a bit. Here we see a plot of calculated vitrinite reflectance versus calculated transformation ratio for the 19 Draupness samples. using the kinetics as they were published. Now, this slide and all of the others are color-coded in a standard way, where the red colors represent the highest published A factors and the purple colors represent the lowest published A factors. Here we see there's a range of about 3 orders of magnitude between the highest and the lowest A factors. We also notice something quite interesting, which is that the samples with the highest A factors, and also therefore the highest activation energies, generate at the highest vitrinite-reflectance values. That is, they generate latest, whereas the kinetics with the lowest A factors and lowest activation energies generate fastest and earliest at geologic conditions. Remember, all of these calculations were carried out at a geologic heating rate of 3 degrees Celsius per million years. Please also notice in this plot that the vitrinite reflectance value at any of our thresholds, beginning, peak, end, for oil generation, can vary by 0.4 to 0.5% RO, depending upon whether the A factor chosen in the multi-run kinetic data analysis was high or low. The 19 Draupner samples were analyzed by a number of different laboratories over a long period of time. That may account for at least some of the variation in the kinetic parameters and in the results. The Oxford clay example shown here, in contrast, was analyzed in a single study over a short period of time by one laboratory and shows rather optimal conditions for detecting analytical uncertainty and quantifying it. We see a very similar result, however, qualitatively. The samples with the highest A factors and highest activation energies in red generate latest, and those with the lowest A factors and lowest activation energies generate earliest. The Green River Shale, shown here, presents another problem: variations in organophases. There are different facies within the Green River Shale, and not all samples labeled Green River Shale are necessarily from identical facies. All of these were simply called Green River Shale in their publications, so we've lumped them together. But again, we see the tendency for samples with large A factors, high A factors, to generate much later, and samples with low A factors to generate much earlier. Finally, the Mata coal provided 10 samples analyzed by a single laboratory, but it divides into 2 distinct organophases. One of them had 6 samples, the other 4 samples. The differences are shown by the dashed lines versus the solid lines. Once again, although there's a narrow range of A factors used, the ones with the larger A factors generate later, and those with the smaller A factors generate earlier. Here we see the very different activation energy distributions for the 2 organophases types within the Mata coals. The rather symmetrical traditional type 3 hill on the left, and the slightly more type 2 appearing distribution on the right. I want to revisit now the compensation effect, this time focusing on the temperature issue. If we first look at the compensation effect during lab pyrolysis, which is where we get the data that we will use to give us our kinetics, the actual temperature at the peak of pyrolysis is probably around 484 degrees Celsius, which is 757 degrees Kelvin, which is the number that is used in the equation. And if we say that we could get the same pyrolysis rate using two different combinations of A and E, as shown on the next line with the K value, the reaction rate constant, equaling two different versions of the Arrhenius equation. And we assume that the original A factor, A1, is 1E14, and A2, the alternative A factor, is 16 times as great, 1.6E15. Then, in order to get the same rate for an activation energy for the original case of 54 kilocalories, the activation energy for the second case must be 4.16 kilocalories higher, or 58.16 kilocalories. These two solutions will give us essentially identical fits under laboratory conditions. But if we now take these kinetics determined under laboratory conditions, high temperature, and use them in a geological simulation where the temperature is only 140 degrees C instead of 484 degrees C, and use the same A and E combinations, we find out that the example with the lower A and the lower E is now going 10 times faster than the other one. Whereas under laboratory conditions, they were going at identical rates. This is a huge difference, and it is very important, therefore, to get the best possible combination of A and E in order to apply it for modeling purposes under geological conditions. Therefore, differences in AE combinations that may seem harmless because they all fit the laboratory data quite well, when applied under geologic conditions can give very, very different results. And therefore, these are not harmless little differences. They have the potential to greatly distort the results of your modeling, and therefore we should pay particular attention to trying to get a best estimate of the true AE pairs to be using in our modeling. And that point leads to another insight into a useful property of the compensation effect. Remember, the compensation effect simply says that you can get the same reaction rate constant using an infinite variety of AE pairs. The compensation effect then becomes the key to converting one set of AE values to any other desired set. And the equation shown in red here is, in fact, a very simple equation that can be easily applied to convert a published data set or any other data set into a more desirable A factor and the associated activation energies. So now we're going to try a little experiment. This again is the plot of calculated vitrinite reflectance versus calculated transformation ratio for 250 kerogens using the published kinetics. Here's the other half of our little experiment. Here we have plotted the calculated vitrinite reflectance and calculated transformation ratio for the same set of 250 kerogens, but this time we have converted the published kinetics into new kinetics using a single standard A factor of 2E14 and adjusting the activation energy distribution correspondingly when that change is made. We see that the clustering is much tighter than it was in the previous example, suggesting to me that a lot of the variation in the published kinetics may be the result of poorly selected A factors. But that's too many samples to look at in detail altogether. So we're going to look now at our special kerogens that were analyzed multiple times. I'm going to start with the Draupne here, and as we see in the upper left, we have the Draupne curves from as published kinetics, and in the lower right, we see the Draupne when we adjust all the A factors to a common value of 2E14. The clustering is much tighter, and very significantly, in my opinion, the color preference rainbow effect has disappeared. In other words, the results do not depend upon an arbitrarily chosen A factor. They are depending upon the natural scatter due to analytical error and natural variation, rather than to an artificial variability that we've superimposed in our choice of AE combinations. Here is the same plot for the Oxford clay, as published in the upper left and adjusted to a standard A factor of 2E14 in the lower right. Here we notice that we may in fact have gone too far in our adjustment, because what we see is that instead of being slow, the red samples with the original high A factors are now going fastest. So instead of mixing completely the samples with different A factors, we now seem to be introducing a bias where the ones that were originally slowest are now fastest. And that might suggest that correcting to a single A factor might not be the best possible solution. Much of the variability in the Green River Shale disappears completely when we adjust the A factor. Clustering among the Mata coal samples has also become tighter using the adjusted A factor than it was using the published ones. But what would happen if we chose a different standard A factor? Previously, we looked at 2E14. Suppose we made it 1E13. Here we see a comparison between the Draupne samples adjusted to 2E14 and adjusted to 1E13. We see two things happening. First, the clustering is tighter when we lower the A factor. Second, the vitrinite-reflectance value at which oil generation occurs is lower when the A factor is lower, just as we had discussed before. You could see that easily because the point of the red arrow is at the same point on both plots. We see the same result for the Oxford clay, although the clustering hasn't changed very much because it was already very tight. But we do see again a lowering of the vitrinite-reflectance value at which oil generation occurs when we lower the A factor. The Green River Shale also shows a slight improvement in clustering with the lower A factor, and again, an increase in rate so that it generates earlier with the lower A factor. Reducing the adjusted A factor even further from 1E13 to 1E12 for the Oxford clay mainly results in a lowering of the vitrinite-reflectance values at which the oil generation window appears. The change in clustering is very small. And as we might expect, raising the adjusted A factor results in an increase in the vitrinite-reflectance values at oil generation and also decreases the degree of clustering, as we see here in the example for the Draupne comparing adjusted A factors of 2E14 and 2E15. I think we'd all agree that using a single adjusted A factor for all kerogens results in a significant narrowing of the hydrocarbon generation window. But there are still two major problems that must be addressed. First, the RO values that define the hydrocarbon generation window depend critically on which A factor we choose. So how can we know that we're using the best A factor? Second, the use of a single A factor tends to lead to the samples with the highest unadjusted A factor generating earliest. Does this seem logical? And that brings up a suggestion that a number of people have said. Why adjust to a single A factor? Why not adjust to a range of A factors? Perhaps we could use different A factors for different samples. But how wide should the allowable range be? Should it be several orders of magnitude, or should it be somewhat narrower than that? In 2013 and again in 2016, I suggested that a range from about 8013 to 4E14 for A seemed reasonable to account for natural variation in A. That was a bit of a seat-of-the-pants estimate, but I haven't changed my opinion very much about that range. And in this study, I've tried out a similar range of values. If you're going to vary the adjusted A factor, you've got to have some kind of rule for how much adjustment to make and what your target is. The idea presented here is that if you do a multi-run analysis that suggests a high A factor, that result might be an indication that the true A factor is in fact higher than normal. However, I think the magnitude of the true variation is probably a lot less than that obtained by allowing A to vary freely. So I developed an empirical equation that converts the A factor from the multi-run analysis, so for example 2E16, to one to be used in modeling, for example 3.8E14. In this case, the transformation represents a substantial decrease in A. Conversely, if the measured value of A was low, that is like 1E13, it would be increased to 6.4E13. And then I applied that method to the samples in this study. This plot, which we've seen before, has all the A factors adjusted to a constant value of 2E14. This plot, in contrast, allows A factors to vary between 2.4E13 and 1.1E15. That is a narrower range than the measured range, but considerably wider than having a single A factor. And in fact, the clustering is tighter. The range of variation of most of the samples is about 0.5% RO, as shown by the double-headed vertical red arrow here. And just for reference here, I show the published range without any adjustment, showing that our adjusted with variable values is a vast improvement over the original collection. For comparison again, this is the published set of curves from Waples and Marzi in 1998. Again, the variation is on the order of 0.5% RO in earliest and latest generation. It's therefore clear that kerogens generate oil at quite different vitrinite-reflectance values depending upon their composition. Therefore, it's very important to know something about the kerogen type in formulating kinetics for any particular kerogen. We've seen that there is considerable variability in the plots of calculated vitrinite reflectance against calculated transformation ratio for the large number of kerogens in our database. There are three main reasons for this data scatter. First, analytical errors in the pyrolysis process and technical differences from one laboratory or one worker to another. Second, natural variation in kerogen chemistry and the structure of kerogens. And third, different methods for derivation of kinetic parameters from raw pyrolysis data. There are numerous ways in which analytical errors and differences in procedures can play a role. Sample handling and preparation can vary from lab to lab. Temperature control within the pyrolysis instruments is imperfect, and the measurement of the absolute temperature is not completely accurate. We have imperfect transport of hydrocarbons from the pyrolysis area into the detector. There could be effects related to the size of the sample selected for analysis, and so forth. To study this phenomenon, I've selected the Oxford Shale with a very large number of samples analyzed by Peters and his co-workers. I've divided the Oxford Shale samples into three organophases, at least for the purposes of this discussion. They're shown on this plot in three different colors, where we've plotted the hydrogen index versus the Tmax. You'll notice first that the Tmaxes are all very low. These are extremely immature samples, with many of them having Tmax values less than 400. And we'll discuss that issue later. But what I have done is I have selected only the blue group at the top. The blue samples all fall along a trend line in which the hydrogen index starts very high for the least mature samples in the far upper left and decreases significantly even in the pre-generative stages to the most mature samples from these outcrops. It's important to understand that this increase in Tmax and decrease in hydrogen index do not represent maturation in the sense of generating hydrocarbons. These kerogens are all pre-generative. However, I believe that there is an evolutionary trend in kerogen structure that is developing during the pre-generative stages, when processes such as elimination of water, carbon dioxide, cyclization, and possibly even aromatization are changing the kerogen structure radically and thus changing the Tmax value. But that's a topic for a completely different video. This plot shows the calculated vitrinite reflectance versus calculated transformation ratio for the 25 samples that fall in what I've called organophases 1, the blue samples on the previous slide. This set of data has been color-coded here by Tmax values, with the purple colors and blue colors representing the lowest Tmaxes, that is the least evolved kerogens, and the red colors representing the highest Tmaxes, or in my view, the most evolved kerogens. We notice a trend similar to what we have seen before, that the most evolved kerogens in red generate hydrocarbons latest, while the least evolved kerogens with the lowest Tmax values generate earliest. The previous slide showed calculations carried out using the published kinetics. This slide shows the same kerogens with the calculations carried out using adjusted kinetics where the A factor varied depending upon the original A factor. The color coding here refers to the original published A factor. We see there's not a clear trend of a relationship between the vitrinite reflectance value during generation and the original A factors. This slide shows the same plot with the red arrow superimposed to indicate the total variation in calculated vitrinite reflectance for all of these organophases 1 samples at peak generation, that is transformation ratio of 0.5. Here it appears to be about 0.09% vitrinite reflectance variability in the position of the peak generation window. But if we return to plotting the color scheme based on Tmax, we see that within any narrow range of Tmax values, for example, from about 380 to 390 degrees with the dark blue and purple colors, the total variation is only about 0.04% RO at peak generation. This suggests that that's an absolute minimum for the type of reproducibility and accuracy that we could possibly anticipate under the best conditions, where the kerogens are completely homogeneous, the laboratory is completely consistent in its methods. That is, we know the calculated RO at any level of the oil generation window to plus or minus about 0.02% RO. That's actually quite accurate. For the Mata coal shown on this slide, the variability is slightly greater. For each of the 2 organophases, the total variability at peak generation is about 0.07% vitrinite reflectance. The Mata coals, like the Oxford shale, were analyzed by only one laboratory with consistent conditions. The Green River Formation, however, has been analyzed in many laboratories by many workers. These samples from the Mahogany Zone come from a number of different laboratories and show a greater variation even after adjustment of the A factor. The total variability at peak generation here is 0.11% vitrinite reflectance. This suggests that we've got to be careful about using published data in general because laboratories will have somewhat different techniques and produce somewhat different results. And therefore our confidence level is going to be slightly lower than if we have many samples generated by one laboratory. To summarize, for the Oxford clay, where we've tried hard to minimize variations in kerogen type and have done the best processing possible, which are extremely immature and apparently of variable degrees of pre-generative evolution of the kerogen structure, we know the percent RO at any desired transformation ratio to within about 0.045%. However, within a single range of Tmax values, the grouping is a lot tighter, with uncertainty in RO being closer to 0.02%. This figure probably represents the minimum uncertainty we could achieve under optimal conditions. For the Mata coal, with fewer samples but probably higher pre-analysis maturities, both organophases showed slightly smaller variations in percent RO of about 0.035%. These variations and uncertainties in both the Mata coal and the Oxford shale probably represent analytical limitations that would be very difficult or impossible to eliminate. For the mahogany zone in the Green River Formation, which is very homogeneous, the variation is slightly higher, plus or minus about 0.055% RO. I think the higher variation in vitrinite reflectance here represents greater variability in lab technique and equipment, since the analyses were carried out over many years by several different laboratories. I believe the variation in these Green River samples could probably be reduced to plus or minus 0.04% RO by working with a single laboratory. A second factor is natural variation in kerogen chemistry from sample to sample. Source beds are not perfectly homogeneous, so no two samples will ever be completely identical. Different organophases, even if they're recognized and exist, are often combined within a single data set. And differences in kinetics don't always correspond to variations in other geochemical properties. The Oxford clay is apparently not completely homogeneous, but we were able to create a homogeneous organopheces 1 by selecting the samples that were represented with the blue symbols in a previous slide. Those plot in a rather tight cluster as shown in the upper left here, with variability of about 0.045% RO, plus or minus. The Draupne, in contrast, shows much greater variability. Here we see that the total variability is more like 0.13% RO from one sample to the next. In other words, the greater heterogeneity of the Draupne is reflected in greater variability in the kinetics, and therefore greater uncertainty in the appropriate kinetics to use for any particular sample. As we have seen, the Mata coal is not homogeneous, but when we separate it into the two organophases, each of them is quite homogeneous, with uncertainty levels in vitrinite reflectance being about 0.035%. The Green River shale, in contrast, as a heterogeneous unit, is susceptible to mislabeling, careless identification, or lumping of different organophases, as shown in the lower right here, where a number of samples that were all simply called Green River shale clearly do not yield identical kinetics and therefore don't represent the same organophases. The final issue in data quality is the methods used in deriving the kinetic parameters from the raw pyrolysis data. There's not really much difference between the multi-run and the one-run method in terms of accuracy if the data reduction conditions are the same for both. The big question is whether to fix the A factor to a specific value or to allow it to be chosen freely by the data reduction software. I won't address that question here, that's a separate topic. But there are a number of other issues that should be addressed. For example, the question of whether or not to extract the samples or whether or not samples have been extracted and how to compare them with unextracted samples. A second point is the possibilities for manual editing of the derived kinetics to account for baseline drift or any kind of contamination. And finally, the question that we have touched on with the Oxford shale, the fact that truly immature samples can be immature and differently evolved from each other and therefore don't all represent the same kerogen. So how do we handle that question? This slide shows pyrograms for a single sample that was analyzed both before extraction, that is at the top, and after extraction. You'll notice the Tmaxes are identical and the main S2 peak appears to be very similar. We notice that the S1 has disappeared in the extracted sample, and also some of the early S2 has disappeared. Now, S1 is not important because that's never included in the kinetic analysis, but the early S2 material, what I call heavy bitumen, has a big role in the kinetic analysis. On this slide, we see unedited kinetics derived from both versions of the same sample. The unextracted is the top, the extracted is the bottom. The most obvious difference is on the left side of the activation energy histogram, indicated by the yellow arrow on both. The unextracted sample has a number of contributions down between 45 kilocalories and 50 kilocalories that come from that heavy bitumen portion of the S2 peak, whereas the extracted sample does not show that contribution. As one might expect, there isn't much difference out at the heavy end, suggesting that most of the high activation energies are legitimate in both samples. However, one edit that I do recommend always is to trim off the final activation energy, because it often is including combined effects of baseline drift and other portions that create problems with the analysis. So I would eliminate the highest activation energy for both of these samples. Editing can be performed on newly analyzed samples, but it can also be done on published data or any data you obtain from any earlier source. That can be done manually using the same principles I'm discussing here. I'd like now to return briefly to the Oxford Shale, where we have a large number of samples with a very wide range of Tmax values. Looking again only at the organophases 1 samples, shown in blue, I think we would all agree that we expect the ones with the Tmax values in the 380s would be less mature than those with Tmax values around 420. But that's in fact not true. The ones with the low Tmax values are what I would call less chemically evolved, but that doesn't correspond to lower thermal maturity. How do we know that? Well, we'll look at the next slide. The Oxford Shale samples analyzed by Peters and co-workers came from 5 outcrop locations located in a swath across England. I think it's safe to assume that the thermal history of all samples at each location were very similar. But in fact, surprisingly perhaps, the Tmax values of samples at each location are highly variable, as shown here. Of the 5 sample locations, only one, Quest, with only 4 samples, has reasonably consistent Tmax values. At the other locations, Tmax values are highly variable. And I interpret this to mean that the degree of chemical evolution and perhaps microbial evolution is quite different from sample to sample. That would suggest very local control on diagenetic processes. But it also means that the character of the kerogen is somehow different at each of the samples, even though the thermal history has been very similar. We've already seen on this slide that if we use kinetics derived from samples with Tmax values in the 380s, we will get hydrocarbon generation very early at low vitrinite-reflectance values. and the reflectance value at which generation occurs increases as the Tmax of the samples increases as a result of the changing kerogen structure, illustrated by the Tmax values. But the maximum Tmax in the data set provided by Peters and co-workers is 421 degrees. So how high must the Tmax be before we can confidently use the kinetics as representing those of a normal, immature, ready-to-generate kerogen? Would it be 425, as I read once many years ago? Would it be 430, 435, or some higher value perhaps, where the kerogen is still immature? That's a question we don't know the answer to, but it does suggest that the kerogens in the study by Peters and co-workers should not be used for calculating timing of hydrocarbon generation, because none of them has a Tmax value that would be close to the normal one at the start of oil generation. The Oxford shale samples are not the only ones in the literature that were extremely immature. Many published Kerogen Kinetics are known or suspected to be derived from extremely immature samples. The question of whether those kinetics are valid for use in modeling hydrocarbon generation is open and needs further investigation. So now I'd like to list some conclusions that I would draw from the material we've discussed thus far. First, the oil generation window that we obtain using all the kerogens where the A factors were allowed to vary freely seems to me to be too broad. Second, the oil generation windows we get using a constant A factor for all samples or allowing the A factor to vary over a relatively narrow range are much narrower than the windows with the freely varying A factors. Third, the generation windows for individual kerogens are still narrower than those for all kerogens and are controlled by analytical error, natural variation, and the methods we used in deriving our kinetic data from the raw pyrolysis data. Fourth, it's very clear that at least some knowledge of kerogen type is essential in defining the hydrocarbon generation window for any kerogen or source rock we're interested in. Fifth, if we really want to model hydrocarbon generation accurately or know the generation window accurately, we must actually obtain data for specific kerogens. Sixth, if we want to determine kinetics accurately for any kerogen or source rock, we need to analyze multiple samples because any individual analysis will have certain irreducible errors. Seventh, the lower the A factor we use for our kerogen, the narrower the hydrocarbon generation window will be. Eighth, lower A factors will result in earlier generation at lower vitrinite-reflectance values. Ninth, simply minimizing the width of the generation window is not a good way to choose an A factor because the absolute value of the vitrinite-reflectance at which generation is occurring is also very important and is not taken into consideration if we're simply looking at the width of the window. And finally, in my opinion, a good method of choosing A values has not yet been published. You'll notice that the last four conclusions have all focused on the question of how to choose an A factor and what value we should use for an A factor. So our final question is, what value should a typical A factor actually have? 1E12, 1E14, 1E16? Should it be a range of values? And to answer this question, in my opinion, to decide on A, we've got to calibrate calculated transformation ratio against measured transformation ratio and let these results guide us in choosing appropriate A factors or a single A factor. But how to do that? I think that this could be, and indeed should be, the next revolutionary research project in petroleum geochemistry. That we should learn how to choose A factors by calibrating the relationship between transformation ratio calculated from kinetic modeling and from the measured hydrogen index. Hydrogen index is the key here. Mark Tobey and I have showed how to do this. Our presentation is available on the internet, and I'm going to very briefly touch on a couple of highlights in that presentation that are the key to implementing hydrogen index in this study of A factors. Although it's well recognized that hydrogen index is related to transformation ratio for any kerogen, very little use has been made of hydrogen index as a reliable quantitative thermal indicator. If we were using it, we would probably envision a linear relationship between transformation ratio and hydrogen index for any kerogen, as shown by the colored lines in this diagram. But these comments and this diagram refer to unextracted samples, which are what we normally work with. But Mark and I showed that if you work with extracted samples, which we believe is the only reasonable way to use hydrogen index as a thermal indicator, these lines are no longer straight but curved. And that curvature, which can be quite extreme at high hydrogen indices, makes all the difference. We showed that transformation ratios calculated from hydrogen indices from extracted samples are systematically significantly higher than those calculated from unextracted samples. And that means not only do we get a different and more accurate picture of transformation ratio from working with extracted samples, but that it's more optimistic. Here, for the Niobrara Formation kerogens at 4 different locations with 4 different maturity levels, the lower transformation ratio in each pair came from the unextracted sample, while the higher one came from the extracted sample. If I were going to carry out this study, I'd choose a group of source rocks with well understood burial and thermal histories, with maturities ranging from immature through all or most of the oil generation window, and with predictable or even constant immature HI values. I'd build careful 1D models and calculate transformation ratio using the proposed kinetics for that source rock. I would measure the extracted hydrogen index for all modeled source rock samples. I'd assign an original or immature hydrogen index, HI0. I would then adjust the source rock kinetics used in my modeling until I achieved optimal agreement between the transformation ratio obtained from the model and the transformation ratio calculated from the measured hydrogen index of the partly mature sample. And then I would repeat this study for several other source rocks to confirm that these conclusions are not limited to just the source rock I happen to choose. Here's a list of some possible candidate source rocks for such a study. You probably have your own favorites or could add others to this list. They all have in common that they're rich source rocks and that they have relatively predictable or constant hydrogen indices for the immature samples, and thus Hi0 is quite predictable. To summarize, my version of the oil generation window for all kerogens is fairly broad, with an apparent range of about 0.5% RO from the earliest generating kerogens to the slowest ones. However, a little knowledge about your specific kerogen will narrow the window substantially. But the crucial problem of how to assign an appropriate A factor for each kerogen remains unresolved and will require additional research. Until we solve that problem, we cannot be fully confident about modeling hydrocarbon generation or defining generation windows. Once we learn how to assign appropriate A factors, with proper care and consistency in lab technique, and with kinetics derived from multiple samples, you will be able to define a kerogen's oil generation window to within about plus minus 0.035% RO, and possibly slightly better. Although source rock kinetics is an old topic, this and a number of other interesting and important issues remain fluid. There's room for a lot of new energy and creativity, and good research will make an important difference for basin modeling. Thank you.